So we're now going to talk about a fascinating biological machine, the molecular motor. This epitomizes both the movement that we expect of living organisms and Feynman's idea of nanomachines. Only we understand now that nanomachines like this are driven by fluctuations rather than the cogs and gear wheels of macroscopic machines. These molecular motors require energy, and throughout the cell, energy is supplied to all types of enzymes that require an energy input by this molecule shown here, adenosine triphosphate. This molecule has two more phosphate groups added to it than found in the backbone of DNA, but you will recognize this component here as looking essentially like part of a DNA molecule. So although this molecule looks complex, it's a beautiful example of how nature recycles her successes. So using here a DNA base modified by the addition of two extra phosphates as a carrier of energy in the cell. The source of energy is the removal of this gamma phosphate at the end of this chain of phosphates here through a reaction with a water molecule, once again catalyzed by an enzyme. So this bond is broken here, and you see the formation of two hydroxy groups, so H, H, and O, coming from the water molecule to form from the reactants, which is adenosine triphosphate and a water molecule, the products. This phosphate here and this adenosine diphosphate, ADP, and no water molecule consumed in the reaction. Here is the equilibrium constant for this reaction, and from this equilibrium constant we can calculate a delta G for the reaction, and these are the numbers that I have put them down here. You see that it's on the order of 20 times thermal energy at 300 Kelvin. So a significant amount of energy available from this reaction. I've also listed it here in units of piconewton nanometers to give you some idea of how much work can be done in generating biological motion over a given distance. Molecular motors are often pictured like this as thermal ratchets. So here is one state of the motor, here is a transition state, and here is a state in which, for example, the shaft of the motor has rotated by a certain number of degrees. It's referred to as a ratchet because once this transition state is reached, dropping down into this second well here prevents a backward step. And so that's shown schematically here as this monomolecular ratchet. This is actually far from being the best description of a molecular motor. This bimolecular ratchet, which is shown here, is somewhat better, but I'd like to draw this out in terms of the type of reaction coordinate plot we've become used to now throughout this book. So if we draw the free energy of the system of reactants and products here versus a reaction coordinate, which for a molecular motor I will take to be the rotation of the shaft of the motor if it's a rotary motor, and we'll talk about various types of motor in the next module. So here is the motor at some equilibrium position. ATP will bind the motor, and because it binds stably, it results in some metastable energy configuration here. It turns out that in some motors, if the total rotation is 120 degrees, this may occur at 60 degrees here. So this is now the motor. This is the motor plus bound ATP. And then finally, the hydrolysis of ATP drives the motor back to the motor alone plus released ADP at the final angle of 1 step of rotation.